In this video, we'll explore exponential and logarithmic functions. Now, an exponential function is a function in the form of f of x equals b raised to the x, where b is our base, and it has to be greater than 0 and cannot be equal to 1. When we graph it, you'll see it has that exponential curve to it. And if our x value is positive, you can see that the growth is going to occur, so it's going to go trend upwards. Whereas if the x was negative, it would be considered an exponential decay, it would trend downwards. And what we have here is e to the x, which is a special exponential function. But that base value can be anything greater than 0, but not 1. In contrast, the logarithmic function is looking at the function of f of x equals log base b of x, where b can be any number, again, greater than 0, but not equal to 1, and x has to be greater than 0. When we think about that, it's equivalent to the form of x is equal to b raised to the y. And what it actually creates is the inverse function with that base. So if we look there, in this case, we know that the natural log of x is the inverse function of e to the x. Some helpful logarithmic properties that you will find as you're working with logarithms especially is that we know that the log base b of x equals y is true if and only if b raised to the y equals x. We know that e to the x is the inverse of the natural log of x. If you have two numbers being multiplied inside a log, we could add their two logs. And if it was divided inside the log, we can subtract the two logs. An exponent inside can be multiplied to the log on the outside. And if you have an issue where your log, where you're not sure about how to find log of a with the base b, you can always find a common log and do the log of a over the log of b. And you can use any log, log base 10, log base 2, even natural log if that helps. So let's look at two basic simplifications. So say we had the log base 16 of 64. Now off the top of my head, that seems kind of confusing. So what I could do is use that last rule that was just shown, and I could look at the log of 64 over the log of 16. And it doesn't matter if I make it base 10 or natural log or whatever, it'll still allow me to get the general idea. So what I want to do though is see if I can find a way to cancel out my logs. So let's break them down, each of 64 and 16, into their exponential factors. So what I find is that I could say that they're both 4 raised to the power. 16 is 4 squared, 64 is 4 cubed. Now using the other property, I can take my exponent and pull it to the front of my log, and I get 3 log of 4 over 2 log of 4. Well, log of 4 over log of 4 cancels, which leaves me with 3 halves. So I know that the log base 16 of 64 is 3 halves. Now say I get a problem like this. Looks very complex, but the idea is still the same. I want to see how can I slowly simplify and get it to something that's easier to solve. The first thing I would do with this problem is say, well, I want to try to get these terms combined. So first let's get the product out front back up as an exponent. And this gives me 36 and 2. So then since this is subtraction and they're the same base, I can change this to the division of my two terms there, 36 divided by 2. And I know that becomes 18. And what I also notice is that this is log of 3 and this is log of 3. So if I do 3 raised to the log and 3 raised to the log, that'll cancel and leave me just with what's inside the logs. So in this case, the 3 cancels the log base 3, this 3 cancels my log base 3, 18 would equal x. So if I plug 18 in here and use the calculator to calculate it, I could simplify this expression and simplify this, and it will come out as exactly the same value. Now how does this apply in the real world? So here's an example of where both logs and exponential values or functions can come into play. Cars depreciate in value often using an exponential decay function, and one such model that can be used is where v equals c times the product of 1 minus r raised to the t power, where v would be the current value of the car, c is that original cost, and r is the rate of depreciation, and t would be the number of years since that was purchased. And that the reason we don't actually plug in exact numbers here is because this could change depending on the type of car, the original cost, the number of years, so we want to have flexibility with our formula here. So in this case, say we're looking at a Ford Escape, and it has a depreciation rate around 15%. So if I bought it for $32,000, how long would it take to be worth half that original cost? So let's look at what we have here. We have the formula. Now we know the original cost is $32,000. We know our depreciation rate of 15%. Well, if the value is going to be half, I need to think about, well, what would that mean? That would mean, well, half of my original cost would be $16,000. And what I want to know is, well, how long does it take me to get to that $16,000? So let's plug in the components we have. 16,000 equals 32,000 times the product 1 minus 1500ths raised to the t power. So I simplify that and I get 1/2 equals 8500ths raised to the t. Well, this is not easy to solve, but what I have to recognize here, since I can't really solve it in any way that would make sense quickly, I need to convert it to the logarithm, and that's how I'm going to solve this problem. So if I rewrite this as a logarithm, I know that t is going to equal the log base 8500ths of 1/2. Now that seems weird again, but I can use that rule where, since it's a weird base, I can do the division of two logs, and I can look at the log of 1/2 divided by the log of 8500ths. And while I may not be able to get a very neat and tidy answer for that, I can at least use my calculator or some other device to help me find those two logs. That is possible. Whereas it's not very possible to figure out how to start with 1/2 equals 8500ths raised to the t. So that's where those properties can come in handy. And that means that it would take me about 4 years and 3 months before my car is worth half of its original cost.